This video will cover section 8.8, improper integrals. Now, in the past when we found a definite integral, that is, with limits from a to b, it really requires that the interval from a to b be finite. So the fundamental theorem of calculus when we were taking the integral and we say f of v minus f of a, it requires also that f be continuous. Okay, so finite and continuous are conditions that we have to have in order to take a definite integral. However, there are some integrals that we call improper. That is, they are not finite or they are not continuous on the interval. So integrals that do not satisfy these requirements are called improper. In an improper integral, either one or both of the limits of the integration are infinite, or f has one or more infinite discontinuities somewhere in the interval of integration. So some examples of what this might look like. In part A, it's really easy to determine that because you see infinity sitting in our limits of integration. So that's an improper integral. So think again about what integration means. It's finding the area under the curve. So if I'm finding the area from 1 to infinity, then I'm adding up the area under this curve as x approaches infinity. So at first, you'd think that that area would be infinite, right, if that continues on forever and ever. However, in some cases, that is not the case. You will approach a finite number. Now, sometimes you will approach infinite area, but sometimes you do approach finite area. Okay, the other type of improper integral is a little bit trickier to find. So in part B, you're looking for discontinuities or sometimes vertical asymptotes inside the interval that you're looking at. So looking at B, the first one, you see 1. This is not continuous at 1, or not. It does not exist at 1. So then how would you find the integral there? And then also for part B, this one does exist from -2 to 2, but it does not exist at x equals -1, which is in the interval from -2 to 2. Okay, so before I always gave you definite integrals that were defined on the entire interval, but now you have to watch out for that. So just to kind of see what this looks like, consider the function 1 over x squared, and we're going to integrate from 1 to b being some unknown number. So if we took the integral of this really quickly, I would rewrite this as x to the -2. And then when we integrate, we get -x to the -1, evaluate from 1 to b. And then when we evaluate, we get -1 over b minus a -1, which would be +1. And we could also rewrite that as 1 minus 1 over b. Okay, so that would be the expression if I took the integral of 1 over x squared from 1, and we have a graph here, from 1 all the way to some unknown b. Okay, so that would be the area. Now, think about that b. So in the next part, think about that b as going towards infinity. So another way of writing this, so if that b is approaching infinity, I have an expression for the area under the curve as it approaches some number b. So think of this, if I'm approaching, if b is infinity now, think of this as a limit. Okay, so improper integrals you need to think of as a limit because yeah, where x is approaching infinity, but if we take a limit, then we could approach some finite number. So if I think of this as a limit as b approaches infinity, so as that keeps going on and on and on, then what's the limit of that integral? Which we already found this piece here to be 1 minus 1 over b. So what we're really finding is the limit as b approaches infinity of this integral we already found, 1 minus 1 over b. And if you calculate that limit, you would get 1 minus 1 over something approaching infinity. So that would really be 1 minus 0, which is 1, which is actually finite area. Okay, so just kind of to recap that, what we're going to look at for this lesson, this is really going to be lesson 8.8a, the first part, because we're just going to be looking at improper integrals with infinite limits today. So that's really looking at this part A piece of the examples of improper integrals. Then in the next video, 8.8b, we're going to look at when we are not existing at our limits. Okay, so First of all, if you are approaching finite area, then we call the integral is convergent if the limit exists. Okay, so if we have finite area, then we call that interval convergent. And then if the integral approaches infinity or oscillates, or in other words, the limit does not exist, then we call that integral divergent. So if you look at numbers 1 and 2, we have, first of all, a to infinity. And then in number 2, we have from negative infinity to b, and then we have a case where we have both sides are limits of infinity. So notice we're replacing the infinite bound by a or b in calculating that limit that way. Notice if we have from negative infinity to infinity, we have to split it into two different integrals. Okay, so let's try some examples. So next we have the integral from 1 to infinity of 1 over x. Now notice in the first example we did, we had the integral of 1 over x squared, which looks like that. And notice for 1 over x, you don't have to know the graphs of each of these really, but it's kind of interesting here. So notice the graph of 1 over x is actually a very similar curve to 1 over x squared. So we're doing very similar here calculations. So we're looking from 1 to infinity. So again, it looks very similar. All right, but when we actually calculate it, it will be different. All right, so first of all, our upper limit is what is improper about this integral. So I'm going to make it proper by turning this into the limit. That upper limit, I would call that b. So I'm going to call this as b approaches infinity of the integral from 1 to b. So that upper limit gets replaced with, think of it as some kind of constant of 1 over x dx. Now the integral of 1 over x is natural log of x, and we're going to calculate that from 1 to b. Now, here at this step, you're not taking the limit first, you're going to evaluate first and then calculate the limit. So this is going to be the limit as b approaches infinity of natural log of b minus natural log of 1. All right, and I can actually drop the absolute value here because you're going from 1 to infinity, so it's always going to be positive. All right, so as b approaches infinity, as the natural log approaches infinity, that's approaching infinity. And of course, the natural log of 1 is 0. So this is actually infinite. So this is infinite area. Therefore, we call it divergent. So I think that's interesting in that how two very similar shapes, 1 over x squared in the first page and 1 over x, actually one is convergent and one is divergent. And it's really about how quickly that line here approaches 0. In the first example, we have 1 over x squared, so what's happening is that line is approaching 0 a lot faster than 1 over x. Whereas 1 over x is approaching it much slower, and therefore it then ends up being infinite area. Okay, another example, we have the integral from 0 to infinity of e to the negative x. So first of all, before I start integrating, I'm going to rewrite this as the limit as b approaches infinity of the integral from 0, replace that infinity with a b of e to the negative x dx. All right, now continuing on, keeping that limit in front, now we're going to integrate e to the negative x, which is really easy. It's just e to the negative x. Evaluate from 0 to b, then plug in b and 0, and we get negative e to the negative b minus a negative, so plus e to the 0. All right, so now as b approaches infinity, we have e to the negative infinity. And remember, the graph of e looks like this, and so as x approaches negative infinity, the graph is actually approaching 0. So this would be 0 and then plus 1. So this is actually a convergent improper integral that approaches an area of 1. Okay, for our next example, we have a slightly different improper integral where the lower limit now is improper, is negative infinity. So we're going to call that a. So when we set up our limit, we're going to say the limit as a approaches negative infinity, and then the integral from a to 0 of 1 over x squared plus 1. Hopefully you recognize this integral 1 over x squared plus 1 is arctangent. So so we can't forget that. So this is the limit as a approaches negative infinity of arctangent of x from a to 0. Then evaluate. So we have the arctangent of 0 minus the arctangent of a. Okay, so arctangent is the inverse of tangent, so it means at what angle is tangent equivalent to 0, which is just going to be 0. All right, now where this gets a little tricky is a approaching negative infinity of arctangent of a. So that is as arctangent approaches negative infinity. Now, arctangent is, remember, the inverse of tangent. And so it's very helpful to remember the graph of arctangent. So that's one of the ones that I would recommend you know. So arctangent, the inverse of tangent, is going to look like this, where you have these horizontal asymptotes at pi over 2 and negative pi over 2. And remember, the limit as x approaches infinity or negative infinity is the definition of a horizontal asymptote. So if this is looking at as a approaches negative infinity, so as arctangent as x approaches negative infinity, then it's actually approaching that value of negative pi over 2. Now don't forget, you also have this negative here, so it's going to be the negative of the negative pi over 2, so then you get pi over 2, which therefore this is convergent. So improper integrals I see a lot with arctangent, so make sure you have this graph memorized for arctangent. Okay, we're going to do one more, and then the rest we're going to do in class. So this last one, we have the integral from 0 to infinity of sine. So that is my upper limit b of sine. And then the integral of that is negative cosine. All right, so then when I evaluate, you get this. Now, cosine of 0 is 1. And so I have the negative cosine of b plus 1 as b approaches infinity. Now, cosine as x approaches infinity is just going to oscillate. It's going to go up and down. A lot of people think it's approaching 0, but it's not. So again, if you have an oscillating function like this as x approaches infinity, then the limit actually just does not exist. It does not equal infinity, does not equal 0, it just does not exist. And actually I did a double verb there. That's one of my pet peeves. It does not equal does not exist. It just simply does not exist. And it's important to know why it does not exist due to oscillation. Okay, so again, it's a divergent improper integral, but it does not approach infinite area. It just simply does not exist. So, and that's kind of what this last little paragraph says. The improper integrals in examples 2 and 5 diverge for different reasons. So let's go back to number 2. That one was also divergent, but I want to actually erase it a little bit, but it diverged because it had infinite area. It actually, when we calculated the limit, it approached infinity, so it had infinite area. Whereas the one in number 5 is divergent because of oscillation. All right, so it is important to recognize the difference between those. Okay, so now 6 and 7 we will do in class.